Welcome back. Today we're going to be talking about atlases, sometimes known as Atlantis or something dumb like that, but that's wrong. They're called atlases, and they are very important for understanding smooth manifolds. A CK atlas, usually just called an atlas, on a locally Euclidean space M is the set. We're indexing over alpha, so there's many of these pairs in here, which are charts. So it's a set of CK compatible charts that cover our manifold. What is CK compatible? That means the transition function from one of these charts to another is CK differentiable. It has K partial derivatives defined, and we want that the collection of open sets here, when we take the union over all of them, give us the manifold. So that's what it means for a collection of open sets to be an open cover of our manifold. I guess I should have put that R and open cover of M. But you get the idea. That's it. That's an atlas. It's just a number of charts that cover the whole map. Just think of it when you have... I don't know how old the viewers are who watch this video, but when I was growing up, we had maps that were in books, and you would have certain pages that covered certain areas of the globe, if you think about it, if you scaled it up. And so even though you didn't have an entire picture of the Earth, which you wouldn't necessarily want anyway, you could put all of these pictures together, and sometimes they would overlap, but they would agree where they overlap, and when you put them together, you get a map of the entire space, the entire Earth. We want to be able to talk about the entire manifold, so this whole thing better cover the entire manifold. Now, I'm going to show you an example that'll make this very straightforward. Okay, so let's go back to our buddy the circle. The circle is S1. We can define it as all x and y in R2, right? This subset of the plane, such that the sum of the squares is equal to 1. We talked about this guy before in an earlier video, but here's an open set where all of the y components of the points in our circle are positive, and here is our homeomorphism. So together these guys make a chart. Here's another one. We just took the negative when we thought about the inverse. Stop and think about all of this if this is confusing, but I talked about where these come from in the last video, so if some of this is confusing, go back and watch that other video, or you can pause here and just think about it. But we have these nice homeomorphisms, and we have these nice open sets, and if you take the union of them, if you take the union of these two, you get the whole circle minus 2 points. Right? Minus where the x-axis would cross the circle. Again, I haven't drawn the axes because manifolds exist independent of coordinates. The circle is still a circle regardless of whether I put an xy axis in. I talk about the circle here in terms of particular coordinates, but this is just one way to describe it to a person. The circle, again, still exists independently of any coordinate system. So that's why I don't have one here, but you can imagine one in your mind. But not to worry, even though we're missing these 2 points, U3 contains one of the missing points, and U4 contains one of the missing points. They contain a lot of other points that were already accounted for, but that doesn't matter when we're taking unions if they overlap like that, because it will still give us all of S1. So the union of these 4 give us S1, which is what I'm writing down here. So we have open sets that cover S1, they're an open cover, and each of those open sets has a homeomorphism, so open set in some sense gets upgraded to a chart, open set with a homeomorphism. So then we have 4 charts, and we need to check whether they're CK compatible. It's actually very straightforward to check whether they are, but I will leave that up to you if you're worried. And you can just pick 2 of them, say phi 1 and phi 3, compose one with the inverse, compose the other with the inverse, and look at the derivatives. On the domains where the sets intersect, right, U1 and U3 would only be looking at this quarter of the circle. Those functions will have some k number of derivatives defined, which you can figure out what k is. It will turn out that these charts are indeed CK compatible charts. So if we take them together as a collection, they form an atlas. An atlas is a collection of charts that cover our space and are CK compatible. Now, there's a special kind of atlas that is of particular importance for smooth manifolds. So if we have an atlas, fancy A, on some locally Euclidean space, we call it CK maximal, or maximal for short. We're going to be dropping all this CK business very shortly. If the only CK atlas it's contained in is itself. And that's just set containment, right? An atlas is a set of charts. So if you have a second atlas is going to be a set of charts, you can just check whether the charts in one set are the same as the charts in another set. And a maximal CK atlas is also known as a CK differentiable structure. So that kind of hints at why atlases are important, because an atlas gives rise to a differentiable structure, which is a much more revealing name, on a manifold. So hopefully that gave you a better idea of what atlases are. As always, thanks for watching. If you have any questions, comments, or concerns, please leave them in the comments below, and I will see you in the next video.